Hello, everybody, and thank you all for coming here today. My name is Sasa Kivisaari. I'm from Aalto University in Finland, and I'm going to introduce our study where we asked how the brain uses bits of information to construct rich meanings of objects. We are all experts in using fragmented information in our environment and understanding its meaning. So, for example, we can easily identify a dog based on the sound of barking or the glimpse of a wavy tail. And as kids, most of us have played some variety of a guessing game. So, for example, if I ask you what is something that has legs, has a thick skin, and has a trunk, most of you will be thinking along the lines of this animal. And we were inspired by these guessing games and thought that it must be a very natural way for us humans to access semantic representations. And we ascribe this skill to a form of semantic pattern completion where we use a set of features to activate a complete representation of a target object. So what we did is that we transformed this game into an experiment, and we devised a guessing game task where we presented the participants with a series of 3 clues, which all described a familiar object. And each object or concept was probed using 6 different sets of clues in order to kind of approach the same concept from different angles. So for an elephant, we would also have asked what is something that is gray, lives in herds, and has tusks. And in the experiment, we had 17 healthy participants perform this task in an fMRI scanner. So schematically, what we wanted to know is what kind of a representation we elicit by probing the semantic representations in this way. So is it the 3 clues that we show? Or is it perhaps some larger set of features associated with the target concept? And we hypothesized is that when we show a set of features to the participants with a sufficient Q validity, then these features serve to activate an existing representation learned by previous experience, which is composed of many attributes related to the underlying target concept, even such that were never presented to the participant. But in order to move on with this question, we needed to ask ourselves, what is the meaning of an object, and how can we put it into numbers? And this we asked the internet. We utilized a 2 billion token corpus of the Finnish internet and applied Word2Vec. And Word2Vec is a 2-layered neural network that maps words to vectors based on sentence context. In this case, it was 5 words previous to the word and 5 words after. And using this method, we got 300-dimensional semantic vector representations for each of the words that we used. And what is nice about the Word2Vec is that it follows arithmetic rules. So one can simply, for example, sum vectors to combine new meanings. So for example, if we sum the vectors of crown and a woman, we would get a semantic representation of a queen. And we took advantage of this feat to formulate our question into a machine learning problem. And we asked which semantic coordinates result in the best mapping with the fMRI data. And importantly, we compared whether the fMRI signal maps the best to the actual clue features that were shown to the participants, or the average of the actual clues words, or whether it better maps to the combination of all possible feature words associated with the target concept. And the set of features that were associated with the target concepts were extracted from an existing behavioral production norm set from Cambridge. And to answer this question, we used a zero-shot decoding model. And we used this model to learn a mapping between the bold signal in each trial and the semantic coordinates of the items in those trials. And in this illustration, the rows illustrate trials, and the column illustrates either the beta value in a voxel for the fMRI pattern or a value of a semantic dimension for the semantic coordinate. And this is a regression-based approach which tries to find the best weights to predict the semantic coordinates based on the activity patterns. And the training was performed using a subset of the items, and for the evaluation we used a leave-to-out classification. So we tested the model with 2 items that were left out of the training, and this procedure was iterated for all possible leave-to-out pairs. We ran these analyses separately for different models. So we used the word-to-vec coordinates for the clue 3 word, for the target word, for the explicit clues that we presented, and for all possible features. And what we first did as a sort of a sanity check is that we averaged across the 6 repetitions of a single target object and used these data to predict the semantic coordinates of the target word. And this model reached a very good decoding accuracy for the target object. The mean was 87%. And this was well beyond chance level and also surprising to us because it was a similar level to studies where people have decoded visual objects. So this, we were really happy about this, and this served as an indication that the task seemed to be working as intended. And in the single trial decoding analysis, we had a more careful look at the content of the resulting representation. And in the right-sided box plot, the decoding accuracies are plotted for each model separately. And as you can see in green, the highest decoding accuracy was achieved for the model where we used all semantic coordinates, combining a rich set of object features, and not only those that were presented to the participant. And this model performed significantly better than the model using the target word, or the combination of the clue words, or the clue 3 alone. And finally, using a representational similarity analysis, we identified regions where activity patterns significantly correlated with the semantic similarity structure of the target concepts used, that's shown in the left. And this analysis really revealed a set of regions where activity patterns seem to contain information about the meaning of the target word. And these regions include the bilateral ventral stream, extending all the way to the very anterior parts, and the bilateral perirhinal cortices. And this is interesting since the perirhinal cortices have been implicated, among other things, in the cross-model integration of object features. And I should note that we could achieve significant item-level decoding also using the bold signal only in the perirhinal cortices. So these results suggest that this region might also play a role in the creating semantic features with existing representations. So to summarize, we achieved a high decoding accuracy for the unpresented target concepts. The neural representations that we elicited with this task seem to contain more information about the target concepts than the literal clues presented, indicating some form of pattern completion taking place. And the ventral stream and the perirhinal cortex may be involved in integrating clues into coherent objects. And finally, we propose that the guessing game is a highly engaging task for accessing conceptual representations. So thank you all for your attention. And finally, I want to thank my team in the imaging language group. And for more information, you can read our paper that was published recently, or come visit me at my poster later today. Thank you.